Hello everyone, welcome to the lecture number 47 of this NPTEL lecture series on charging infrastructure, and in today's lecture we will see the design procedure for the physically realization of the filter inductor. So in the last class we have seen the transformer design procedure where we started off by selecting a appropriate core, and then after that we have defined our core losses and copper losses, and then after that we found out our delta B optimum value for which our total losses in the transformer is minimal, and that will give us the condition which if it is not satisfied then we will go back and then select the next big size core. Once we obtain the optimum value of delta B or peak AC flux density, then we have calculated the number of turns in the primary winding, and after getting the number of turns in the primary winding, we have then calculated the number of turns in other windings, and after obtaining the number of turns in the other winding, we moved ahead and then evaluate the wire sizes which is needed to actually wound the winding. So before that, I mean at starting we have already selected the core which actually satisfy the condition where our P total is less than equal to our P total allow, that means how much power loss in the transformer we can afford to have, and that we will get it by doing the loss budgeting of the overall system, and from there we can able to know what could be the maximum power loss which we can afford to have it in the transformer. And from there we will then reach to a point where we select the core, and once we select the core we can then define the number of turns in the primary winding, because by that time we would have already arrived at optimum value of AC peak flux density. From there we have calculated using the turns ratio given in the specification or obtained from the specification. We can then define number of turns in other windings, and once we know the number of turns in the other winding, we can then evaluate the wire sizes which is needed to actually wound the winding, and that we will obtain it from the gamma j optimum value, that means the optimum value of the fraction of the area which is been allotted to individual winding, and that we will obtain it from the optimization such that our total copper losses in the transformer is at its minimum value. So that is where we have done the transformer design procedure, and once we obtain the transformer we will finally do the design check where we will see that whether the losses in the transformer is less than equal to the allowable losses in the transformer. This is one of the magnetic devices which we are using in isolated DC converter. There is another magnetic devices which are there, if we recall a simple buck converter which comprises of the switch and the diode, and then we have inductor, capacitor and resistance RL, C, L and V in, and output was V naught. So we have seen that our PSFB, which is another buck derived topology, we have seen the full bridge converter which is again the buck derived topology, we have seen the different kinds of converter which are actually having the buck derived topology, where we have one inductor kept at the output of the half bridge. This is done to actually filter out the ripples to smoothen the current which is been coming out of this half bridge. So this is another magnetic device very commonly being used in our power converter or our isolated DC converter. So let us try to see how we can physically realize the inductor, because inductance value we can able to get it from our specification, but how to actually physically realize the inductor, let us see those procedures. So before starting those procedures, let us discuss some of the things related to inductor. So let us take a core which is again we have taken UU kind of core. This part half is U, second part is U. So U core we have taken, and let us say the core cross section area is AC, and from this thing we are actually supplying a current I, and let us say this number of turns is N. So, as a result of this excitation of the current, there will be a flux which will be generated, which will be like in this direction, and which goes through the core and return back to the coil. Now, in this we can then define one more term which is called as the magnetic path length, which is this length of this red color line, which is nothing but given as LC, which is the magnetic path length in the core. And then let us try to calculate what is the inductance of this particular structure. So, for finding the inductor, first we will do a simplest thing, which is we will apply the Ampere's law. By using the Ampere's law, in this we will take the entire loop which goes from this side and comes back. This is the entire loop we will take. So, in that loop, if we apply, let us take the magnetic field intensity in the core to be Hc. So, we can then write HcLc, which is magnetic path length, this length of this entire loop is nothing but equal to the amount of current which is being enclosed in the loop. So, the amount of current is we have I current through one winding and there are n number of turns. So, total current is n times I. In the simplest form we can write this consideration, considering there is no fringing effect of the flux and there is no flux which is leaking out of this core. I mean the entire flux generated out of this coil is actually get confined within the core itself. Now, this is the thing we got where Hc, we can say that the magnetic field intensity inside the core. So, we can then define the second term. From here we can just write the flux density in the core due to the domains present in this core. So, let us say the B value is, or the magnetic flux density which get produced due to the alignment of the magnetic domains in the core is nothing but will be given by B is equals to mu C Hc, where mu C is nothing but mu r times mu naught, where mu naught is nothing but the permeability of the free air, which is nothing but 4 in 4 pi into 10 to the minus 7, and this is relative permeability. Generally, relative permeability is very much greater in thousands or in hundreds. That is when we can say the mu C is very much greater than mu naught. So, since we have the flux density B is equals to mu C Sc, so we can write our flux to be nothing but phi is equals to B times AC, area of cross section of the core, which is flux density times area of cross section of the core. So, that implies flux to be AC mu C Hc, and that implies flux is nothing but mu C AC and I by Lc. So, this is the flux we got from this thing, where here n is the number of turns, I is the current excitation given to the inductor. Now, that particular thing we can then write from here, we can then write flux linkage in the entire loop is nothing but lambda is nothing but equal to n phi, and that gives lambda to be equal to mu C AC n square I by Lc. Now, this implies my inductance. We can write inductance L to be equal to lambda by I, and that will be nothing but that gives L equal to mu C AC n square by Lc. And if we look very carefully, this particular structure, if we try to define the magnetic circuit model of this structure, so we can then write magnetic circuit model from our basic understanding of magnetic circuit. We know that it will look like we have one voltage source having the value equal to Ni, which is MMF, and that is actually been connected to a reluctance term called as the RC, which is the reluctance offered by the core. That means reluctance is nothing but the resistance offered to the flux which is being built in the core. So, this is the flux which is been flowing through the core. So, it is nothing but a magnetic circuit model similar to that of the voltage source connected to a resistance and which lead to the current to flow through that particular loop, and that we can then define from doing the electrical equivalence. We can then say the flux is proportional to current, RC is proportional to resistance, or you can say the reluctance is proportional to the resistance, and MMF is proportional to the voltage applied. This is the electrical equivalence. So, then we can then write simply flux phi is nothing but MMF by reluctance of the core, which we can then write MMF and I by RC. Now, if we take, let us define, in the previous slide what we have defined, let us take this is equation number 1, let us take this is the equation number 2. So, from 1 and 2 we can very well say reluctance offered by the core to the flux is nothing but equal to LC by mu C AC. And this, if you recall this one, let us say this inductance value which is just defined by equation number 3. So, we can then say, and let us say defined by 4, from 3 and 4 we can then say inductance is nothing but equal to N square by RC. So, we can then say if we know the equivalent reluctance offered to flux path using this reluctance, we can calculate inductance of any complex magnetic structure. So, using this formula which is N square number of turns divided by reluctance offered to the flux path by the complex magnetic structure, we can easily calculate the inductance corresponding to that complex magnetic structure. So, let us try to insert one air gap and then let us see how the inductance calculation will vary in case we introduce the small air gap Lg, where Lg is the air gap length which is been introduced in this particular core, and this is nothing but my N, number of turns N, and I am exciting with I, and which will generate the flux phi, and this LC is, again we can define the same LC. This is my LC length, magnetic length LC, this entire thing, and I can also define my area of cross section of the core to be nothing but area which corresponding to this. So, let us take area offered by this air gap is nothing but AG, we can write area of cross section offered by air gap. So, in this case we can then define the reluctance offered by the core as well as we have now inserted the air gap. So, there is another reluctance which is introduced because of this insertion of this air gap. So, we can then define this magnetic circuit model to be Ni, and then we have one reluctance offered by the core and then the reluctance offered by the air gap, and those two are connected in series because both see the same flux going through them. So that is why if you try to draw the magnetic circuit model, it will look like something like this, having the same flux which will be seen by the reluctance of the core as well as by the reluctance of the air gap. So that is when we can then write my flux to be equal to nothing but Ni by reluctance Rc plus Rg, and that I can then define flux to be equal to Ni by, we can write Lc by mu c Ac plus Lg by mu naught Ag. Here we assume that flux which is coming through this will actually cross this air gap and get into the core. However, there are some fluxes which actually gets fringes out, in this manner, and that is why we can say that my AC is nearly equal to Ag, but AC is not equal to Ag. So these two terms are nearly equal but not exactly equal to each other. Now using this one, the overall equivalent reluctance, if we put, it is nothing but Rc plus Rg, and that is when we can then write my inductance of this complex structure is nothing but N square divided by R equivalent, which is nothing but equal to N square by Lc by mu c Ac plus Lg by mu naught Ag. Now we can then take another approximation, because we know that our mu c is very much greater than mu naught. That is when we can say that in this term we can say that Rc is very much smaller than Rg, because Rc reluctance offered by core is nothing but Lc by mu c Ac, and reluctance offered by air gap is nothing but Lg by mu naught Ac. So because of that, my Rc value is very much smaller than Rg, and that is when I can, in this particular denominator term, this is very small going towards 0, and that is when we can say that my L is nothing but N square by Lg by mu naught Ag, and that is when we can say L is nothing but mu naught Ag times N square by Lg. So the entire inductance is only due to the air gap length and the area of this air gap and number of turns of this winding and the mu naught, which is mu of the air gap. If you look very carefully in the previous part, whenever there was no air gap, it was mu c Ac N square by Lc. Here it is mu naught Ag N square by Lg. So we can see that because of the insertion of this air gap, the entire inductance is only dependent upon this air gap dimensions. The core has no role to play when the moment we put the air gap. But because of this thing, we also see that this inductance which we get by this value is very much less than the inductance we got without putting this air gap, because our mu c is very much greater than mu naught, and that is when we can say that the inductance which we got when there was no air gap is pretty much larger as compared to the inductance we got with the insertion of the air gap. Now let us take how the BH curve will get changed. So if we draw the BH curve, we know that BH curve of us, where we can also define the phi h curve, phi h curve if we define, which is nothing but a flux versus a magnetic field curve, if we see, which is nothing but B times AC, which looks like a straight line going from 0 to some point, and then it becomes saturated, and this is the, we can say this is a phi saturation. So this we have assumed, this curve is drawn with assumption of that the non-linearities are absent. So if we took this one, this is the Ni, or you can say this is the Ni max, after which my core will get saturated, or you can say after which the relationship between B and H is no longer the straight line and all the magnetic domains get fully aligned. Now if we see the the slope of this curve is nothing but equal to, if we see this is phi versus H curve or phi versus Ni curve. So if we take from equation number 1 phi versus Ni curve, if we say it is nothing but slope is nothing but 1 by Lc by mu c AC. Since my mu c is very much bigger, this value is smaller, that is when the slope is larger, and that is when you will see that this curve will reach to the saturation faster. Now when we introduce the air gap, what happens is that it will take the good amount of time to reach to the saturation, and this value is nothing but n I set with air gap, and this one we can rephrase that and we can define that thing to be n I set. So what we see is that since we have the air gap which is been introduced in this, so because of that the slope of the curve of this curve, if we draw, slope is nothing but 1 by Lc by mu c AC plus Lg by mu naught Ag. This you can see from this particular equation number 5. From equation number 5, this will be the slope between phi versus H, which is nothing but equal to Ni. Now if you look very carefully, we know that my mu c is greater than mu naught, and that is when we can say that our Lc by mu c is very much lesser than Lg by mu g, and that is when this particular slope will, we can say that is nothing but slope with air gap is nothing but mu naught Ag by Lg, and that is when the slope is proportional to mu naught, and that is when the slope value is very small. That is when you see the curve will reach to hit the saturation value only after reaching to a new value of I sat g, and there we can say that I sat g is greater than I sat value, is very much greater than I sat value. What it indicates that when the air gap is introduced, there are things which happens. First, the inductance value goes down. Second, if we see very carefully, one important thing which will happen is that, say, the current at which, the second thing what happens is the current at which the core saturates increases. That means you can now allow more current to flow through the inductor without going into the saturation. And fourth thing is the inductance with air gap is nothing but, we can say, mu naught Ag n square by Lg, and inductance without air gap, if we recall from previous slide, it is mu c Ac n square by Lc. If we introduce the air gap, the inductance value of that particular magnetic structure is actually independent of the core dimension. So we can say that inductance is independent on the core dimensions. Now this is the third thing which will happen. So when we have any inductor which carries both DC and AC, we generally use the core with a air gap introduced in them, as a result of which what happens is that it can able to carry larger value of current before going into a saturation, and as well as what happens is that the inductance becomes independent of the core dimensions. So in case when we have the buck converter which is like this, now if we take this one and if we assume to be having a CCM operation, so continuous conduction mode operation, that is when we can say that my inductor current, when my switch S is on, that means let us say if I draw dTs period for dTs period, this is up to Ts period, that means up to dTs period, when my switch S is on, at that point my voltage across inductor is V in minus V naught, and that is when the inductor current will rise, because we know that our V in is greater than V naught as it is a buck converter. So what we will see that the inductor current will rise linearly with the slope nothing but equal to V in minus V naught by L. And in this point S is off, and that is when my D is on. S is off, that is when D is on, in order to ensure the inductor current gets a freewheeling path, and that is when we see that inductor current will falls down with the slope equal to minus V naught by L, and this will continues like this. Now if we take very carefully, the ripple content which is there in inductor. Now this ripple content is is delta I. Generally delta I is less than 10% of I, so we can say that delta I is very much smaller than I naught. Before that, let us also draw one simple thing. For this one, our magnetic circuit model will be looking like we have Ni and we have Rc, we have Rg, reluctance due to the air gap. So this is our magnetic circuit model we got, which is nothing but the MMF Ni is imposing on this series connection of reluctance offered by the core and the reluctance offered by the air gap, and we can then write the MMF drop happens across the Rc to be equal to Ni across C is nothing but from the Ampere circuit law HCLC, and this is nothing but my overall flux which is going, which is Ni by Rc, reluctance of core plus reluctance of air gap multiplied by the reluctance of the core, and that is when we can say my HC Ni by R, the reluctance offered by core plus reluctance offered by air gap multiplied by reluctance offered by core divided by Lc. If we take the average value of this current is nothing but I naught, and thus we can obtain the H naught value corresponds to the average inductor current, which is nothing but I naught is nothing but N I naught by Rc plus Rg times Rc by Lc. So now we can then plot our BH curve, which is like this, and let us take at this point my Hc or H naught which is coming, which is nothing but N I naught Rc by Lc, reluctance of the core plus reluctance of air gap, and then over that we have our nothing but the ripple I naught ripple which goes like this to this here like this. So if we try to draw our ripple in this manner, and on this side ripple to be drawn on this way, then we can then see our curve will look like going in the top and going at the bottom. So it will look like something like going here, comes like this, and then goes here. So this is this is something like curvy shape it will look like. So only this much is the area which is been enclosed in the BH loop, and that will actually be corresponding to the very small area enclosed in BH loop is very small. And since this area enclosed in the BH loop is very small, we can then say because of that the core loss associated with the core material is very small. Since my area enclosed in the curve is very small, the core loss associated with that is very small, and it is primary because the ripple in the inductor current is very small as compared to the average value of inductor current. So now let us try to see whatever the understanding we got related to filter inductor. What we have seen is that since the area enclosed in the BH loop is small, what we can say that the core loss in the inductor is negligible, as the area enclosed in the BH loop is very small. Second thing what we can say is that since the ripple in the inductor current is very small, we can also say that the AC winding resistance is also negligible. So, we can also say that since the ripple component in inductor current is small, we can say that the winding AC resistances, that means the resistances corresponds to the skin effect or resistances or the increased resistances due to the skin effect and proximity effect is negligible. This resistance is due to this. So, then we can say that the flux density will now need to be chosen based upon the saturation value of the magnetic flux density which the core material can have. So, is chosen based on saturation value. That means for the selected core material that will have a corresponding B sat value. So, we must ensure that the flux density whatever we are getting in our inductor has to be less than this B sat value, or you can say the maximum flux density what we can have in the inductor during the operation of the inductor must be less than the saturation value of the magnetic flux density. Similarly, we can say one more thing we can say, as we have understood that air gap is employed to avoid saturation. So, now these are the things which we have understood while doing the discussion related to filter inductance, and since we are introducing the air gap, we need to know the air gap length. Since we are obtaining the flux density based upon the saturation value of the flux density value, so we have to know what could be the maximum value of flux density we should keep in, and then we should also know what will be the core sizes we have to select, and at the same time we should also know what will be the number of turns we needed to obtain the required value of inductance value. So, we can then obtain the filter inductor design. Now, if we see the filter inductor design which has the fixed DC and a very small ripple current over it. Here the design outcomes are same. The core size defines the core cross sectional area, AC, the window area which is WA, same as what we have seen the window area in the case of transformer. If you see the U core, then the window area will be this area, only this part of the area. That means what you can say that if this is looking from this thing, if this is the core, then this is the window area we are talking about. And then again the mean length per turn, because the first turn will be on one side wall of the core and the other winding will be on the next wall of the core. So, the mean length per turn will be somewhere in between that, and that way we can calculate the mean length per turn, and we have seen in detail how we can calculate the mean length per turn in the last lecture as well. And then we have to also find out the magnetic path length, which is nothing but defined by LC, and our this mean length per turn is defined by MLT. Then after finding out the core size or core dimensions, one need to also find out the number of turns. Let us say if we are introducing a air gap, then we also need to know what will be the air gap length, and once we know the air gap length, to realize the required value of inductance, we must have the required number of turns. So, in that way both are interlinked to each other, and then finally we must know how much will be the size of the wire such that that many required number of turns will get accumulated within the window area. So, these are some of the design outcomes which we need to find out in order to physically realize the inductor, because inductor just like a transformer also has the winding and the core which will be sitting on the bobbin, as we have seen in the last lecture. Now some of the specification we will be provided. For example, we will be knowing what will be the required inductance we wanted to actually physically realize, because that will actually determine the number of turns, some of the core dimensions, wire sizes, air gap length. And then we will also define what will be the allowable power loss we can actually accommodated in our loss budgeting of the entire converter. So what we do is we generally do the loss budgeting of the entire converter, and then we say that this much is the amount of power loss I can allow from the inductor. So the allowed power loss is nothing but P is equals to I square R, because here the core loss is very negligible, since the area enclosed in the BH loop is very small, as our ripple current is very small. So we can say that the loss in the inductor is only due to the copper loss, and that we can say it is nothing but I square RMS times resistance. And this resistance is, again, since the magnitude of the AC excitation is very small, so we can say that the resistance is nearly similar to that of RDC, or the resistance due to the DC excitation. That means which is nothing but we can say rho L by A, where L is the length of the turn and A is the area of cross section of the wire. We will see that as we go along. And then finally we must also know what will be the maximum current, because that will actually determine what will be the size of the wire I can select. So these are the design outcome we must get, and these are the specification which we have in our hand. Now considering this particular structure, let us try to define the magnetic circuit model, which will look something like this. Now this will implies I can write down this to be my Ni to be nothing but flux multiplied by Rc plus Rg, and as we know that our Rc value is less than Rg, we have already discussed in previous slide, we can then write our Ni is nothing but phi times Rg. That is when we can say that the Ni for the maximum value of the inductor current is to be nothing but my phi max times Rg, because Rg will not change, as Rg value is nothing but your Lg by mu naught Ag. And once you select the core and once you define the air gap length, your Rg value will not gonna change, as the Rg value depends upon the dimension value. So we can then write this one to be nothing but Ni max into B max ACRG, and this particular thing we can then write from this particular expression, we can then put the Rg value to be nothing but AC Lg by mu naught Ag. And since if we assume that my AC is very much closer to Ag value, or you can say the area of cross section of the core is very much closer or is very much near to the Ag value, that means we have assumed that if the fringing of flux through the air gap is very less, so we can then say that our AC is nearly equal to Ag, and that is when we can then write Ni max is nothing but your B max Lg by mu naught. So what we have understood is that depending upon this I max value, the B max value will vary, and we have to ensure that whatever B max value we are getting, or the maximum flux density which is obtained in the core during the operation of the inductor, has to be less than B set value. That means we can say that the maximum flux density must be less than the B set value. So from this particular expression, if you know your Lg value, if you know your number of turns, if you know I max value, you can able to understand what will be your B max value, and this B max value you have to ensure that this B max value is less than the saturation value of magnetic flux density. So this is how one can decide on what could be the value of B max. One can keep it, for example, the B set value for the ferrite core cores are generally kept somewhere around 0.25 Tesla. So you can then take your B max value, somewhere between 0.2 to 0.22, and that is when you can then understand, depending upon what will be your Imax value in the inductor, depending upon the circuit operation in which inductor is been kept, you can obtain the Imax value, and from the Imax value you need to ensure that this Lg is and number of turns is kept such a manner that the Bmax value is less than the Bset value. So that is one of the check one has to ensure. So that is why this is one of the condition one has to see whenever they are actually selecting the core size for the filter inductor design. Then the constraint number 2, which is associated with the inductance, we know that the moment we insert the air gap in the inductor, and we are inserting the air gap because we wanted to avoid saturation. So the moment we insert the air gap, we know that the inductance is only due to the air gap, and since we know that the fringing effect is neglected, so we can say that our area of cross section of the core is nothing but equal to Ag, and that is when my inductance is nothing but equal to mu naught Ac n square by Lg, where Lg is the length of the air gap and mu naught is the 4 pi into 10 raised to power minus 7, which is the permeability of the free space. Now this is my constraint number 2, which is related to the inductance value, and this inductance value, because we have inserted the air gap to avoid the saturation, this inductance value is actually only dependent upon the air gap. Now we know that this is our core, and here we are putting the winding, and so our if we see our winding area or window area, if we take our window area will be nothing but equal to this part. Only in this area I can accommodate the turns, and since if we have n number of turns, which is one of the unknowns we have to calculate, if we have n number of turns, then the total area taken by copper conductor will be n times Aw, where Aw is area of cross section of the wire used for winding. And since this winding is accommodated or housed in this window area, it is like this, it will be drawn like this, one after the other, like this it will be arranged. It will be arranged like this in the core, like this. Now if we take this to be straight line, then our things will be much better. This is our core, and in this entire area we are actually putting all our windings. So this is housed in that one, and since we know that in the window area, because since we are using circular conductors, these conductors are placed where, even if they are placed nearby each other, it is this area which is not been consumed. So that is when there are only portion of area which we can use out of this window area, and that is when we got this term which is called as the winding fill factor, and which is nothing but greater than equal to NAW. Similarly, we can also define the winding resistances, because winding resistance are the one which will actually determine the required area of cross section of the wire which has to be used. So we can write resistance of the winding to be rho L by AW, where AW is the cross section of the wire, area of cross section of the wire. This is what I am talking about, AW. L is the length of the wire, and we know that since we have the winding going from this side to this side, so this is mean length per turn. We can then write this particular thing R to be N times R to be rho times N MLT divided by AW. Now this is the number of turns we are using, N, where here N is number of turns. So we can then calculate the mean length per turn and then multiply that mean length per turn by n number of turns, and that is when we can get the overall resistance of the winding, and this is, we can say that AC effects are neglected AC effects are neglected, like skin effect or proximity effects are neglected, because we have a very small percentage of ripple in this current which is used for exciting this particular winding. So, we have very small AC component. So, in summary, what we can do is we can write down the 4 things what we have obtained. The first thing what we have obtained is nothing but the relationship between the I max and B max, which is given by this. Let us say define this as equation number 1, and here we ensure that the B max value is should be less than B set value. Now, the second thing what we have obtained is the inductance due to the air gap, and that inductance value what we get is nothing but mu naught AC n square by Lg. This we can define equation number 2. This is inductance due to air gap, because in the structure what we have assumed where we have introduced the air gap. So, what we get is the inductance is primarily dominated by the air gap, and after that we have then also obtained the things related to winding area, where we obtain that KUWA must be greater than equal to NAW. That condition we have obtained, and this we can define it to be the equation number 3. That means the window area which is been there has to be greater than the amount of area which is be taken by the wires which are used while making that particular winding or while realizing that particular winding. And finally, we have also obtained the things related to the winding resistance. What we have obtained value is that rho times n times MLT, which is mean length per turn divided by AW. Now, in this if you see, what we have is we have got some of the quantities which we can obtain from the specification and the material of the core which is been selected. For example, we know our Imax value, this we can obtain by understanding the circuit operation in which this filter inductor is been used. Then we know our Bmax value from the core material. We know that what can be the Bmax value, it should be less than the saturation value of magnetic flux density. So, generally for if you select the core material, you have already defined what could be the maximum value of B which you can go. Then after that you can then define, we also know our mu naught value, which is nothing but 4 pi into 10 to the minus 7. Similarly, from the specification and from the circuit operation, we know what will be the inductance value which we have to obtain. Similarly, we also know what is our winding field factor. Again, this is a constant which is defined for a required kind of winding which we are doing, and then we also know our maximum resistance which we can allow in our winding from the specification. That means the amount of loss which is been allotted to the transformer. So, from there we can know what is our winding resistance value we can afford to have, and we also know our rho value, because depending upon the material of the wire which we have selected, which we have already defined in the last class. So, these are the quantities which are obtained from specifications, core material and circuit operations. However, whatever things which we do not know is nothing but is the number of turns which we have to do in the course to obtain the required value of inductance value. Similarly, what is the magnetic path length which we needed, the MLT, the mean length per turn for the core which is been selected, the window area which is required in the core, then what are our area of cross section of the core, and the area of cross section of the wire which is to be used to wind the turns such that to obtain the required value of inductor. So, these are the things which need to be known, these are unknowns and we have to somehow know them. So, what we can do is we can rearrange, let us define this as equation number 4, we can rearrange equation number 1, 2, 3, 4, and we will get relationship which is nothing but AC square WA divided by MLT has to be greater than rho L square I square I max divided by B square max times RKu. Now if you look very carefully, in this particular relationship what we get is these are the specified values, that means which we can obtain either from the specification or from the circuit operation in which this particular filter inductor has been kept, and this left side quantity is nothing but the core dimensions. And let us define this particular equation to be nothing but equation number 5. Now this is one of the important conditions which will help us in actually determining what will be the core size which we can select. Now let us try to understand the inductor design procedure. So in the inductor design procedure, the step 1 will be select the core. Now while selecting the core, we have to select the core in such a manner that the core is large enough to ensure that our condition which is mentioned in equation number 5, which is AC square WA divided by MLT, has to be greater than rho L square I square divided by B max square RKu. So we need to select the core in such a manner that this particular expression must be greater than equal to the expression in the right hand side. Now this expression is from the specified values, that means from the circuit operation and from the specification we know all these values, and then after knowing all these values we have to select the core in such a manner that the core will give you the value like LC, AC, WA, MLT value after selecting the core, and once you evaluate this term, and this term has to be such that this is greater than this particular thing. So this condition has to be met, and we need to select the smallest core whose dimensions satisfies whose dimension means whose core dimension, that means your LC, AC, WA, MLT value satisfies the condition in equation 1. So once we select a core, for example, if let us say we decided that we will use the ferrite material, and in ferrite material let us say we choose a particular E type of core. So we will start with E5, E10, E25 and so on, because you have different this thing, let us say E45. So you will select the core, and for individual core we can calculate this expression, and we must ensure that the expression in the left hand side must be greater than equal to the expression on the right hand side, which is been actually defined by the specification or the circuit operating condition. And the smallest core which satisfy this particular condition, we will select that core. For example, let us say we have select the E5 and we saw that this condition is not met. Then we go ahead and select the E10, and then we will see if this condition is met or not. If let us say if this condition does not met, then we will go and see the E25 core, and if this E25 core condition is met, so we will select that E25 core, and that will actually will give us the things like our LC, AC, window area and mean length per turn. And once we know these particular things, we will then move ahead and then calculate our number of turns. For that, what we can do, we will just use a simple relationship which is Li is nothing but n times phi, and that implies my Li max is nothing but number of turns times B max times AC, and that implies my number of turns is nothing but equal to Li max by B max AC. So using this expression we can say that the number of turns to be used is nothing but n equal to Li max by B max AC. Also we need to ensure the units of these particular quantities. If they are in SI units, then all the things should be in SI units. Now, after defining the number of turns, we can then select the next important thing, which is the air gap, because we are considering that we are using a core with a air gap. So, we have to now use the air gap, because why we use air gap, because we can then avoid saturation of the core material. So, that is why air gap is introduced. So, this air gap value can be not given directly as mu naught AC n square by L. Now, here we know our n value, we know our AC value from the selected core, and we know our inductance value. From there we can calculate our the length of the air gap. Again, depending upon the units of this quantity, one must have to ensure that the Lg value is defined either in meter or in centimeter, that one has to ensure that. So, this is way by which we can calculate the air gap. So, the first step is selecting the required core, the second step is defining the number of turns, now the third step is defining the air gap, and then after that comes the step number 4, which is evaluating the wire cross section area, which is nothing but AW to be less than equal to KU WA divided by N. Now, here again we have to ensure that whatever the unit of this WA, the same will be the unit of AW, and then using this AW value we can select appropriate, we can select wire having required AWG or SWG values, or you can say the required wire gauges. Again, here we have not considered the AC effects like skin and proximity effect, because we have assumed that the ripple in the inductor is very minimal, and that is when the effect of the AC resistance in the losses is minimal. So, here we have not considered any AC effects, here assuming no AC effects. So, this is how one can design the inductor, where using this we have obtained the core size, and after obtaining the core size we have defined the number of turns which is required to obtain the required value of the inductance value. After that we have defined the air gap length which has to be introduced. After that we have defined the AW or wire sizes which is needed to actually wound the inductor, and which can handle the required value of the current which is going through the inductor, such that the resistance offered by this wire is below the allowable losses in the inductor. So, using this thing we can define how we can physically realize our inductor, where we have selected the appropriate core size and we have selected the required number of turns. We have also calculated how much air gap length to be introduced, and then what will be the size of wire which has to be used to wound this particular inductor, and that is when one can obtain the inductor. And finally, once we get everything, we know our number of turns. Since we have already selected the core, we know our mean length per turn, and since we have already selected the wire size, we know what is the area of cross section of the wire. From there we can calculate the resistance, and then we can check if this resistance will correspond to loss which is less than the defined copper loss or not, which is nothing but, or copper loss, or you can say the overall loss or inductor loss or not, because the core loss is very minimal. So, this is nothing but we can find out by I square times R. So, whether this value of R is less than this particular defined copper loss or not. If it is not, then we will go back and start our design from the step 1 by freshly selecting slightly bigger core, which will give us the different value of AC, LC and WA, and that is when we can use those AC, MLT and WA terms to calculate the number of turns, and then the air gap length, and then finally select the area of cross section of the wire. And this is the iterative process one need to go and finally obtain the physical parameters related to the filter inductance, and then can physically realize that filter inductance. So, with this we will finish our discussions related to the design steps for the filter inductor. We will see you in the next class with the next set of module where we discuss what are the different charging sequences when the charger gets plugged in. From the communication perspective, from the connection perspective, we will discuss from the next class onwards. Thank you patiently for listening to this lecture.